All right. Afternoon, everyone, and hello, Internet. Great. So I'm Matt Ryall. I'm the CEO and co-founder at Mawson Rovers, and yeah, thrilled to be here today. Thanks to the organisers for inviting us along. I'm going to talk to you about how robots are going to help humans explore space. So maybe a slightly different slant on the human aspect today. We're going to be talking mostly about robots, but we'll have a little bit of information about how we're going to work together with the humans. So first, a little bit about me. So I was originally a software engineer. And I spent 15 years working at a software company in Sydney called Atlassian. It's an Australian tech unicorn, for those that don't know it. Does kind of project management software for technical teams. And I was head of engineering there for Confluence for a long time, and then head of product for Jira Software as well. And so I built a lot of software, and I was looking for something that had a more physical manifestation in the world, and I've been looking to join the space industry for a number of years. And so I was kind of looking for the right opportunity. I spent a bit of time doing a lot of research. I did a podcast about space for a while and interviewed a bunch of people across the industry to try and find out what people are doing, what kind of interesting projects are going on around Australia. And then the right time seemed to appear. So why now? Why did I decide to join the space industry now? The first thing that got my attention was when SpaceX started landing reusable rockets and obviously promising a future where you can reduce the cost of getting stuff to orbit. That totally changes the equation, obviously, for getting stuff into space, building, space stations, sending humans to other planets and beyond. And that's really what first got me excited, maybe like 5 or 6 years ago. And then over the last year or two, we've really seen the development of the Artemis program with NASA and SpaceX and many others partnering up. And the opportunity here is really a mind-blowing amount of mass into orbit and to the moon's surface. So Starship there, which is now the human landing system for Artemis, promises to take 100 tons of payload to the lunar surface, which is a truly massive amount. Like the Saturn V that took the Apollo astronauts to the moon could land an awesome amount. It took over a small little lunar module and even a little rover on some of the later missions for the astronauts to drive around. But that was nothing. It was like 5 or 6 tons, I think, in total, compared to what Starship will be able to bring in terms of real equipment. You're talking about proper mining equipment that can now be transported to the moon, large habitats, things like that. And as you can see in this little render is, we'll have cranes like dumping stuff off by the pallet load onto the moon, which is a totally different vision to, I think, what people were imagining a few years ago. And the last piece of the puzzle for me was the Australian Space Agency, who came into the picture in 2018. And last October, so just over a year ago, they announced their Moon to Mars Trailblazer program. So out of that $150 million program, Moon to Mars program, they said that $50 million, a big chunk of it, would be allocated to a lunar rover development program. And the ambition there was to really define Australia's contribution to the Artemis program and to going to the moon and onto Mars. And the contribution would be the development of a lunar construction rover. So this is a render that the Australian Space Agency put together. It shows, a technology demonstrator, I guess, to start. It's picking up some soil and it's taking it to a extraction facility on the moon. So those three things kind of came together. And at the end of last year, I decided it was time to really move into the space industry. And what I really saw was that for the first time, really since life arose, 3.5 billion years ago, we have the opportunity to take life beyond Earth. And, the sustainable base on the moon is now really something that's quite feasible and going to happen in the next few years. So, I thought this was a unique opportunity. We need to seize this opportunity and really work together. And I see our, my role with Mawson Rovers is trying to bring together people across government, research and industry to try and make this happen. So that's the mission of our company. We decided to focus on robotics and supporting the human exploration of space. And our mission is to build robots to help humans explore space. So a little bit about us. We design, manufacture and build the software for robots, for rovers. We were founded last year. Like I mentioned, we're currently a team of 5 engineers, so just a startup. We're developing our first platform, which we call R1, which is a lunar mobility platform. So the idea is that we have a rover with 4 wheels. It can drive itself around, and then you can kind of put whatever you want on it. It could be like an excavation system. It could be a set of cameras or maybe some like sensors for detecting things about the environment. Could be like a hole digger. You know, anything you can imagine you should be able to put on this small rover and drive around and do what you need to do. As a business, we also do some work with satellites. So we've found some clients who are developing CubeSats, developing payloads for larger satellites as well. And we've also been helping them with hardware, PCB design, electronics, and software and integration as well. So we have a kind of multi-skilled team that working on a number of different space projects at the moment. But the one thing that's taking from my background at Atlassian and in software is we're really driving this from customer requirements. So we're trying to build a business on the back of real demand and needs in the industry, not just coming up with things because we think they're a good idea. So when you look more broadly at like how will robots help humans explore space, I really like this picture that the Australian Space Agency put together. So this shows a potential moon base here with a bunch of activity going on, and you can see a number of ways that robots or robotic vehicles are helping the humans to run this base. So here's just a few examples of things that you can just easily see. There's infrastructure, there's landing pads there, there's habitats. Those habitats need to be positioned and moved around. Obviously, you can't do that by hand on the moon, so you're going to need robots to do that. Air and water, you need to extract from the regolith on the surface, so you want to automate that. Transportation, obviously the Apollo astronauts had their lunar roving vehicle, and we'll need a similar set of transportation vehicles for activity on the moon. Resources, exploration, maintenance, the list goes on. There's lots of potential there, but so far we've found 3 really interesting customer use cases that we're focused on. The first one is, like I mentioned, that air and water extraction from the soil. It's so crucial. It's exactly where the Australian Space Agency has put the focus for their Trailblazer program. They want to go and grab the soil, the regolith, transport it to an extraction facility that NASA builds, and then demonstrate that extraction of oxygen and potentially water as well from the regolith to ensure that astronauts can stay for extended durations on the surface. The second use case we're looking at is mineral exploration. So this shows some hardware that an Australian company has developed called Fleet. And Fleet is talking in their Seven Sisters mission about going and mapping the minerals on the moon. And so we're talking about deploying this, it's called seismic tomography, the sensor on this. And so using that sensor to really get an understanding of all kinds of mineral compositions on the moon. It could be the locations of water, could be the locations of iron or other minerals that we could use for construction, or it could be platinum, titanium, other things that are valuable metals in their own right as well. And lastly, there's also companies around the world developing infrastructure. So this is taken from a company called Astroport, who are developing lunar landing pads. And so they have their own robot that is creating these small bricks and laying them down on the surface to provide a stable landing pad on the moon. And that stops the problem where when the rockets come down, they're not blasting the lunar soil into all the surroundings. And so they've come up with a plan and a way of developing that. And what they need to support that is a whole set of robotic vehicles to transport the soil there, to create mounds of dirt around the landing pads, to create a safety zone, to dig trenches and lay power cables and cover them up again. And so there's an enormous amount of work that needs to be done there with robotic vehicles. And so these are the kind of 3 main areas that we're looking at for our robotic development. And at the moment, since we started last year, we've been focused primarily on the first one. So this is our R1 rover prototype, which we designed for regolith gathering to meet the requirements of the Australian Space Agency. So you can see here some of the key features of the design. It has a 4-wheel drive and 4-wheel steer design with active suspension. So it should be able to navigate and move around on difficult terrain. It all uses precision servo motor controllers for safety and reliability. It's a 20-kilogram class rover. Our prototype at the moment is a little bit heavy, but hoping we can cut that down a little bit with some, maybe put it on a diet, save a little bit of weight, drive it around a little bit, do some exercise. So the idea there is it can transport up to 2 kilograms of regolith in a repeated fashion to complete the mission. And there's plenty of space on board or on the outside to mount on extra tools. And that's where we're expecting partners to help out. So we want to work with people to develop a space-ready excavation system or robotic arms, things like that. Solar arrays, there's actually Australian companies and many international companies developing improved efficiency solar panels for use on the moon, and so on. It's for daytime use only. This design, 20 kilograms isn't quite enough to pack in enough batteries to survive the darkness of the lunar night, but we anticipate scaling up a version that can handle that. In-house, we design and manufacture this and write our own software. Like I mentioned, we have partnerships for many of the kind of external components around it. And really the philosophy behind this was to come up with a maximalist technology demo. So basically looking at all the joints and all the kind of flexibility options we could add into the mobility platform, build it all, test it out, and then see how we can reduce pieces and take stuff away as we test it in a kind of simulated lunar environment. As part of the Trailblazer program as well, we also put together a mission concept design. Our proposal was an 8-day mission. We would perform multiple trips to gather regolith and bring it back to the extraction device that was mounted to the lander. Our proposal was to land at a site called Nobile Crater, which is near the south pole of the moon. And it's the site that's been selected for the Viper mission that NASA's planning in now 2024. And what that means is that we'll have quite a degree of certainty over the landing terrain, be able to pick a spot that has ideal resources in terms of the level of the ground, the access to permanently shadowed regions or dark craters where there's likely to be water, and other areas that might be interesting from a mineralogical perspective as well. So our plan for the mission was to gather 2 kilograms of soil in 100-gram plus increments. And, we had a little plan laid out like this and deposit that for oxygen extraction. We're not just designing stuff, as I mentioned, we're also machining stuff. So here's a picture of our rover under development so far. So we've got, I think, 98% of the parts are machined and built now. So over 150 aluminium custom built pieces. We designed custom gearboxes for the wheels to optimize the drive system, make sure it's efficient and reliable. And we've also been doing testing with our motors to make sure we're getting the right level of torque to drive this machine around, and that it'll also be reliable. And then on the right there, you can see our kind of simulation environment that we've just started working on at the moment to get a simulated rover driving around and test out the joints and how we will drive this thing in real life. So some of the challenges we faced, everyone likes to ask me what are the challenges of building stuff for the moon. A lot of them we haven't actually solved yet, but we've done a lot of thinking and research about them, and we have, I think, access to some of the leading researchers in these areas, both in Australia and internationally. Number one is the vehicle control and autonomy. So making sure the rover doesn't run in or fall in a ditch or something like that, and be a pretty useless mission if we did that. Environmental design and testing, making sure we can stand up to the rigors of the lunar environment, which is probably one of the harshest in the known universe. Human robot interfaces. This is where the humans come in. So trying to work out ways that the robot can interface with the astronauts, the other human members of the system. It could be operators on the ground as well as operators on the moon. So we're going to talk through some of these one by one and jump into a little bit of detail about what we're thinking here. So let's start with the vehicle control. Our high-level plan for this is to have some hazard detection and avoidance in the system. So looking at stereo camera support, potentially LiDAR, although we have some constraints there that I'll talk about in a second. The technology for these kind of things, I believe it's developed well enough to apply this on the rover as it is at the moment. I don't think there's any new groundbreaking research and development we need to do. It's more a matter of, applying some of the SLAM techniques that already exist for identifying things in the environment, making sure that there's also manual, there will be a large degree of manual control, I think, for these early missions. And so making sure that the humans are in the loop, reviewing the obstacle detection outputs before we're planning movements for the vehicle. I think we're also in a good position where the moon has been mapped to a very large degree already, and will be even more detailed maps prepared with orbiters coming online that will map to like the nearest meter or half meter in the next couple of years. Some of the challenges with the autonomy system is really the power usage. So we're looking at less than 40 watts for the sensors and the compute systems on board. And so when you're looking at LiDAR, that actually heavily constrains the number of both even if you can run the sensor itself, but also the volume of points that you can get from the point cloud with the LiDAR. So that's something where we're going to be running, I guess, a number of tests terrestrially, trying to work out what we can use that'll fit in that power envelope. We also need to do a lot of local processing. We can't downlink the video to like a high power CPU somewhere else, or a collection of GPUs in the cloud. There's no cloud on the moon yet. Maybe one day there will be a cloud. But for the moment, we need to do the processing on the computer, which also has to fit inside that 40-watt envelope. So that puts a lot of constraints on the type of, again, hazard detection, hazard avoidance that we can build in. So I think it's going to be a matter of augmenting the manual controls to make sure human operators are not making mistakes. The other aspect here is that the commercial off-the-shelf parts today are not proven in the lunar environment. There are some stuff, high-end cameras and things that you can get that have been used on Mars, but they're extremely expensive. And so, trying to find that balance between cost and space heritage is going to be a tricky balance to strike as well. So talking a bit about the environmental design and constraints, there are kind of three main problems with the lunar environment you need to solve. Dust, everyone loves to talk about dust. Thermal problems, so the temperature range is kind of minus 180 to plus 150, something like that, depending on which area of the moon you're in. Even just looking at daytime use, there's still the aspect you might go into a shadow of something, and then the temperature could fall very quickly to minus 200 degrees. And lastly, there's radiation. So those are kind of the three main problems we have to solve. Dust ingress, we feel, is a pretty well solved problem. So there've been, you can see the Teflon seals here. These have been used on Mars rovers and tested with lunar simulant as well extensively by NASA. They will prove fine for most of the shafts and to keep the internal components safe from dust. There's also a number of dust-resistant bearings and things like that that are available off the shelf, ceramic bearings, quite resistant to dust corrosion as well. So we feel like that's a problem that we can solve with the design and testing. On the thermal side, this is a really interesting challenge with insulation and heat management. This is something, again, where we're going to have to do a lot of testing. I think aiming for daytime use here helps us with narrowing the scope of the stuff that we have to do for these initial versions. But again, we'll be working with thermal vacuum chambers, trying to ensure that the heat load is distributed properly, positioning electronics in the chassis in the right places, and using appropriate materials. And then the rad-hardened hardware as well is a problem we've just started looking into. Obviously, for our terrestrial prototypes at the moment, we're just using off-the-shelf hardware. We're trying to set stuff up in an architecture where we can iterate on those components. So using things that can be adapted to use to coding on an FPGA, trying to start with redundant systems so we can set up a voting algorithm that we can then iterate towards something that's space ready. The challenges with the approaches that we have, mass limit constrains your options in terms of heating, especially as we're looking towards like surviving the night. The number of batteries you can pack into a rover limits the amount of power that you can sustain a heater for over 14 days of darkness. And so there's generally a tight constraint on making sure the operational plan for the rover doesn't spend too much time in darkness, and that we have a clear kind of plan of avoiding shadowed areas where we might lose some electronics or cause problems there. And as I mentioned before, I think with the cost and complexity, redundancy adds some challenges to our software lifecycle and development timelines. And the last thing, so bringing the humans into the picture, I want to talk a little bit about how human-robot interfaces are evolving. Again, I'm not sure how much this will play into our early iterations, where we're mostly looking at manual operation. but I think manual teleoperation, I think from a ground standpoint. But I think as increasingly you see astronauts working in an environment where there's lots of robots, like you saw early on, becomes increasingly important. So there's kind of traditional, what we call kind of traditional human-robot interfaces, which is, using a controller. So you can see here like the Spot robot from Boston Dynamics. It's just controlled with like a little gamepad, typically, and you'll drive it around and do the operations you want to do with it. And then there's a kind of coding or light coding kind of interfaces here, like RoboDK, that are used to program industrial robots. And so these obviously have some benefits, as in you can immediately see the impact of what's going on with the controller, and the coding has the advantage of like repeatability. But both these have major failings when it comes to human interaction. On the controller side, you have to be 100% attentive to what's going on with the robot, so you don't run it into anything. And on the coding side, the operator isn't there when the robot's operating, so it could risk hurting people and things like that. So the more newer HRI approaches that are kind of enabled by deep learning are kind of interesting things where we're trying to use these capabilities to stop robots doing stupid things. So gestures is the first one. So looking at ways that robots can be commanded using gestures or recognize human forms so they don't run into them. This has obviously advanced quite quickly in the last 4 or 5 years. Probably started about 10 years ago with the release of the Kinect. People started hooking those kind of commercial sensors up to their robots. And these days, you can see this picture from OpenCV, which is an open source library for computer vision. It can recognize human poses straight out of the box, and you can plug that into your standard off-the-shelf cameras and computer and get it going. Maybe more advanced now is looking at verbal commands, so telling robots what to do. So there's a fusion now that researchers have developed, combining models for text generation and recognition with robots, and being able to tell the robot to, pick up that box of cereal over there, or go to that hole over there and fill it in. Those are things that are starting to become possible, but they're still in the early research stages, I'd say. Not seeing much kind of commercial traction there. And then even further in the future, there might be the opportunity to have brain interfaces to robots. So this is MIT here experimenting with a kind of sensors mounted on the brain, where what they do is they detect a sharp change in the brain waves of the person that's wearing it. And usually that happens to indicate there's an error, or there's a problem. So this could be, again, because astronauts are so finely monitored in space, this could be an opportunity for where sensors on the astronauts could tell the robot to stop moving if it senses something going wrong with an astronaut's brainwaves or other biological indicators. So what we see here, I guess, is a lot of things on the research side that are really interesting from a product development point of view. And so we'll be keeping eyes on these over the next 5 years, I guess, to see how they mature, other technologies that can be brought into this for industrial applications, like lunar exploration, and really get them to product development stage, because there's a long journey that goes from like, this works in a research context in this finite experiment that we've run, to something that we can deploy, in the real world where, people's lives are depending on it. So just to wrap up, I think my final point is that space exploration, and you could see this in those research areas, really requires collaboration between companies like us representing commercial interests in what we're trying to do, the government support, which is really essential to get space initiatives off the ground. This is a new industry. It doesn't survive without government involvement. This is not something that we can bootstrap just with commercial interests. And then the academic research, which I think many people here represent, bringing that together is really what I see space exploration is all about. And so, we've had several opportunities already at Mawson Rovers to collaborate with universities. We also have had some government grants supporting some of those projects. These are more on the satellite side so far, not on the rover side. But yeah, this is really what I would love to see more as we, go and expand life beyond Earth. Collaboration, working together, and building that sustainable base on the moon. So just to wrap up, I'll say thanks to my teammates, Dominic, Michael, JD, and Scott, and to Douglas Mawson. So Douglas Mawson, who is our namesake and was an Australian explorer of the Antarctic. He explored the Earth's South Pole, and we're going to explore the moons. So thank you very much.
Thanks so much, Matt. Really encouraged to see who your namesake is. Good to connect the dots there. And of course, like many others before you today, these technologies have a lot of application and benefits back here on Earth. So excited to see where you go and what great pedigree and heritage you have coming from Atlassian. So I'm sure that these projects are in really good hands. And so now we have working our way through the space business side of space. I'm now really pleased to be able to introduce to you Kosai Yamashita, who is the Chief Creative Officer from Digital Blast. What a cool name that is. And so Kosai will be talking to us about their work in the software platforms that we're going to need to operate and run these things. I can see a collaboration already emerging between all of our speakers in this session. So if I could please welcome to the stage Kosai Yamashita.